6.6 Geometric Sequences. So geometric sequences are a little different than arithmetic sequences. So let's take a look at, review what an arithmetic sequence is. Arithmetic sequence. And then we'll also put over here geometric sequences. All right, so an arithmetic, remember, had a common difference. And that common difference we said was d. So the equation that we would write would be a sub n equals a sub 1 being the first number plus something times that difference. And remember, it was always 1 less than the number because that's how many differences we had. So geometric sequences is a little bit different. So let's take a look at this example, 1, 5, 25, 125. You probably see it already, but if we take a look at and we think about it as an arithmetic sequence first, we would have to find the plus or minus, and these are pluses because they increase. So plus 20, plus 100. So we can see that there's not a common difference, so there's no arithmetic sequence for that. It is not an arithmetic sequence, so we'd have to look back and add it again. And so I think you can see that it's a times 5 each time. 5 times 5 is 25, and 25 times 5 is that 125. And so that's our geometric sequence, and it's called a common ratio. And the reason why it's called a common ratio is because to get that times 5, what you do is you find a ratio. It's the 125 divided by the number previous to it. And if we look at the lower ones, the 25 divided by the previous one. And then the 5 divided by the previous one. So they all equal times 5. So that's that common ratio. And so we do have an equation for that. It starts off with, of course, a sub n being the nth number or the nth term for our n, and our nth term for our n here. That's our nth term for writing an equation. And we bring down an equals, and we have, so here's the equation for it. It's starting with our a sub 1, but then we're going to be multiplying by our r, our common ratio. Different than our arithmetic where we added our a sub 1, our first term. We're adding those differences. Here we're going to be multiplying our ratios. So let's take a look at it. So let's take a look at our third term. And to get to our third term, we have to take our first number and multiply it by times 5, 2 of them. Oh, so it's 3. The third term has 2 multipliers or 2 common ratios. If we look at our fourth term, it had 1, 2, 3 common ratios. So that would be the number of ratios we would multiply would be to the power of n minus 1. So it has that n minus 1 same kind of idea, but instead of the differences, it's our multiplier. So we show that, and that kind of looks like an equation that we already kind of sort of know. So that would be referenced back to our exponential equation, y equals ab to the x power. But because this is a sequence, we start with our first term, a sub 1, and then that makes it a little bit different than all the others. So now if we were to take and look at graphing this. So it would be good to grab some graph paper. We're going to be in the first quadrant with our sequences because they always go up from 1, 2, 3, and so on. 4 and 5. So we're going to go up here and let's go up by, it's going to go up quickly. So let's go up by, 5, 10, 15, 20, 25, 30, and so on and so forth. So at 1, it's going to be 5. No, 1 is 1. Oh, I got tricked on that, tricked myself. 1 is 1. The first term is 1. The second term is 5. The third term is 25. The fourth term would be way up above, and it's following that same exponential growth multiplied by 5. So as you move over 1, you're going to multiply by 5. Over 1, we're going to multiply by 5. And that's that multiplier. So now if we wanted to find the next 3 terms here, I'm going to put a comma, and we're going to just multiply by 5. We'll do that the next 3 times. So 105 times, or 125 times 5 is 600. 600 times 5 is 3,000. And the next term, the third term, or the sixth term, fourth, fifth, sixth, seventh term is going to be 15,000. So it increases really fast, and that's kind of like that exponential growth kind of idea. But this is a sequence, a geometric sequence. So if we continue for more examples, example number 3. So let's take a look at 1, 3, 9, 27, ... And we want to find the equation or the geometric sequence, and we want to find the 10th term. So there's 2 kind of things we have to solve for, is the equation that we're going to be writing and the 10th term. So we'll start with the equation first, and I noticed that this is a geometric sequence right off the bat, so I don't have to do the dividing the previous one by the previous one. So it's times 3 times 3 times 3, and that will be our ratio, our common ratio of times 3. So I'm going to write down my geometric sequence, which is a sub n equals a sub 1 times r to the n minus 1 power. So a sub n equals, a sub 1 is 1, times my r, which is our multiplier of 3, to the n minus 1. So I can kind of simplify that down to a sub n equals 3n minus 1. And that times 1 here would be our first term, a sub 1. So I kind of like this one. So this right here is my equation. Now I'm going to substitute in 10 when n equals 10 to find my 10th term in our sequence. So a sub 10, so I'll substitute 10 in for n, equals 3 to the 10 minus 1. So a sub 10 equals 3 to the 9th power. Ooh, and that's multiplied by the 1 of the first one. So if that one I probably need to type into my calculator. And so when I type that in, I get 3 times 3 times 3 times 3 times 3 times 3 times 3, and it's 19,683. Doesn't seem like number is divisible by 3, but it is, because if you add up the digits, they all add up to a number that's divisible by 3. So that is our sequence to find the 10th term. So let's take a look at another example of a sequence to write the equation for it and find the 10th term. So we're going to write the equation and find the 10th term. So I kind of notice already that it is not a geometric, but it's an arithmetic sequence. So it's a +5 for each of these. So my arithmetic sequence is a sub n equals a sub 1 plus my difference, and remember it's one less that we have to of those times differences. So we will substitute in, so a sub n equals 5, which is my first term here, plus n minus 1 times my difference, which is our 5 here, difference. So I can simplify that. A sub n equals 5 plus 5n minus 5. So a sub n equals 5n. So that's my simplified equation. And that is what I would write on the answer line if it asked me to write the equation. I could write this one here too. That would be fine also. But this one is a little bit simpler and easier to use. So now when we find that 10th one, so when we say n equals 10, we'll write a sub 10, that'll be the 10th one. So we really don't have to write the n equals 10 here because we've already done that in our equation. When we write a sub 10, that means to the n equals 10, the 10th number in that sequence. So we'll have 5 times 10, which would be a sub 10 equals 50. So there is our 10th term. It would be 50 in our sequence. So our next example is negative 64, 16, negative 4, dot, 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 and continues on. So if we take a look at this one, that's different. We want to write the equation and the 10th term. So let's see. If I subtract those, that would be, no, it's definitely not, because if I look at between the 16 and the negative 4, that'll be different than that one. So it's definitely not. So I'm going to see if it's a geometric. So I'm going to take 16, the number, and then divide it by the previous number. And I'm going to do that same thing over here. Negative 4 and divided by the previous number. So that'll simplify to negative 1/4. So I'm thinking maybe that's my one over here. That's going to be my multiplier. So 16 goes into 16 once, 16 goes into 64 4 times, and it's negative. Ooh, there it is. So it's got the same multiplier, which is our, not difference, but it's the ratio. So it is a geometric sequence, and our formula for that is a sub n equals a sub 1 times that r ratio n minus 1 to the power. So I will substitute in my ratio and my first term, which is negative 64, parentheses, negative 1/4 is my multiplier to the n minus 1. And there is the equation for this sequence, geometric sequence. So now to find the 10th term, we'll just substitute in 10 for n times negative 1/4 to the 10 minus 1. So we'll simplify this. Bring down my 10, a to the 10th equals negative 64 times negative 1/4 to the 9th power. And now I'm thinking, okay, it would be really nice if this 64, this negative 64, was kind of in um, a little simpler way. So I'm thinking and kind of organizing my numbers. So I'm going to do exponent properties here. So 64 is 4 to the 3rd power because I've already kind of thought about that up here. So in previous ones. So that would be negative 4 to that 3rd power because it still makes it a negative here. I'm also going to be doing my exponent properties of quotients. So that would be a over 1 to the 9th power. And I'm going to move that negative down to the 4 to make it the same as the other one, to the 9th power. So now a to the 10th equals negative 4, that quantity to the 3rd power, multiplied by 1 is in the numerator. I have this in the denominator, so that would be negative 4 to the 9th in the denominator. So I know that 3 of them cancel out, and there are 6 left over. They are in the denominator to the power of 6, and there's a placeholder in the top. And then at this point, I would take my calculator because that's a little bit more than my multiplication tables, quite a bit more. And when I type that negative 4 to the 6th power, I get a positive, because it's an even, positive 4,096. And that would be the 10th term in our sequence there. Now, to determine the next one, we have to be a little bit careful in thinking about it. So let's see, we have the sequences 2, 6, 11, 17, dot, dot, dot. And let's see, well, is it arithmetic? So that would be a plus 4, plus 5, plus 6. So there is a pattern, but it's not arithmetic. So let's see if it's geometric. So I'll get my arrows in here for my common ratio, which would be a times 6 over 2, which would be a times 3 for this one. And then times 11 over 6. Oh, that didn't work. And this one would be times 17 over 11. Oh, so it's not geometric, and it's not arithmetic, so it has to be neither. And right now we know that there's probably a pattern to this, because if we look at our arithmetic, there is a pattern to that, and because it's going up, our second kind of difference, the second kind of derivative, we call it, is a plus 1, plus 1. So that's a common difference, but that we're not looking at that second difference yet in Algebra 1. That comes later on in Algebra 2 and kind of that higher level. So right now we can just say it's neither arithmetic nor geometric.